Hi, this is an example problem about work from chapter 6. Pause for a moment and read the question. So we've got an image here of a man pulling a sled with salmon. And we can see that there's four forces there that are actually acting on the sled with the salmon. And the tension force, of course, looks like this, because it's transmitted through the person's pull to the sled. And so we're given a little bit of information here. We know that the magnitude of the tension force here is equal to 100 newtons. We know that the mass of the fish and sled combined is equal to 50 kilograms. And we know that we can calculate the magnitude of the gravitational force from that information. Plugging in those numbers gives us a gravitational force of 490 newtons. And we're also given the coefficient of kinetic friction here. And we're told that the sled is dragged from a coordinate position of 12.4 meters to 18.0 meters. So here we've got 12.4 meters. That's your x value. Here you've got 18.0 meters. And so we can calculate the magnitude of the displacement S. That's going to be S final minus S initial. And that's going to end up being 18 meters minus 12.4 meters, which is going to give us a 5.6 meters for our displacement here. Now, given this displacement and these four forces acting on the sled, we want to calculate how much work is done on the sled by each of those four forces. We don't know all the forces yet, but we can start here. Let's do the first one, part A, the normal force. Now, the normal force and the displacement force, just like I did in my previous video, I'm going to draw the forces. There's your Fn, and here's your displacement, S. What's the relationship between those two? 90 degrees, right? Remember my formula for force, for work done by a force? So this is the work done by the normal force, W sub n, I'll call it. It's going to be plus or minus the parallel component of the normal force to S. And since there is no parallel component, in other words, Fn is perpendicular to S, this is 0. And we have 0 work. Now gravity is going to give us the same result if we draw the gravitational force. And if we draw the displacement, we see that again they're at 90 degrees. Just like with the normal force, I don't need to know the magnitude of the gravitational force either. I can just see that they are 90 degrees apart. And so again, the work in this case done by the gravitational force, it's equal to 0. All right, let's keep going here, and we will look at part C. This is the work done by the tension force. Again, draw the tension force. There it is. We know it's got a magnitude of 100 newtons. No, I wrote that wrong. Not 100 newtons. Should be 150 newtons. So let's go ahead and update this little bit over here. This is 150 newtons. And I'm going to draw the displacement vector again exactly as it appears. There it is, S. Now in this case, I do need to figure out the parallel component of the tension. So here's the T parallel, which we care about. Here's T perpendicular to the displacement, and of course we don't care about this. So to calculate the work, we're going to go ahead and need to figure out if this is a 30-degree angle, what is that T parallel equal to? Well, that's going to be equal to the magnitude, right? Here's the magnitude. It's going to be 150 newtons multiplied by, this is the adjacent side to angle 30 degrees, so this will be cosine 30 degrees. There's our T parallel, and let's put it into the work equation done by the tension. I see that the tension component T parallel is in the direction of S, so I'm going to choose the positive number. And then T parallel itself, I'll just write the whole thing down here. So what we do is because they're in the same direction, T parallel and S, we choose the positive. T parallel is given by 150 newtons times cosine 30 degrees, and then the magnitude of S here is 5.6 meters. Put that into the calculator, and we'll go ahead and get an answer for that. And that comes out to 727 newtons times meters. Now, to do the next part, we need to figure out also something about the frictional force. So let's draw the two to see what the work's going to look like in part D here. So we saw that the kinetic frictional force goes like this. And it's in the exact opposite direction of the displacement. So when we are going to calculate the work here, we're going to notice that, okay, the parallel component of Fk, it's the whole magnitude Fk, right? Because it's already parallel to S, as you can see right here. Now, we also see that they're in opposite directions, Fk parallel and S. So when I write down the formula for work, I'm going to choose the negative sign. For Fk parallel, I'm going to put in the whole magnitude Fk, and then I'm going to put in S, right? Now, the question right now is, what is Fk equal to? We got to use Newton's second law to figure that out. To do that, I'm going to go ahead and note that the magnitude of the kinetic frictional force has a formula, and it's equal to mu k times Fn. And of course we know what mu k is equal to. It was given to us. So we're going to need to figure out Fn in order to get this guy. And let me go ahead and just drag that diagram down, and we'll figure it out quick with Newton's second law. All right, so I've gone ahead and brought the diagram down here, and I've set up just a y component column from the vectors. Now, we know that the kinetic frictional force got 0 in the y, and we know the acceleration in the y direction is 0. And we're trying to figure out the normal force, but all the magnitudes in the positive y direction. We don't know what that number is yet. Gravity, we calculated that it has a magnitude of 490 newtons, and that's all in the y direction, negative. And finally, the tension force. We need to figure out the component of tension that is in the y direction. So here's our triangle, and here is Py, which we can see is equal to 150 newtons times sine, the opposite side of the angle, 30 degrees, right? And if we calculate that, we see Ty is equal to, it's a plus 75 newtons. So we've got this as well. Let's plug this all into Newton's second law. So we know that MAy equals the sum of the force in the y direction. AY is 0, so we got 0 is equal to, we've got plus Fn minus 490 newtons plus 0 plus 75 newtons. So when we solve for Fn with some algebra, we see that it's going to be equal to 490 newtons minus 75 newtons, which is going to give us a value of 415 newtons for Fn. And we can calculate what Fk is now, right? So Fk is going to be equal to mu k Fn. And in this problem, mu k is equal to 0.2, and Fn we just saw 415 newtons. Plug that into your calculator, and we get a value 0.2 times 415 is 83 newtons. Now that we know the magnitude of Fk, we're just going to go back to the formula that we had set up before from our picture and calculate the work done by the frictional force on the sled. So the W, K, it's going to be equal to minus Fk multiplied by the magnitude of S. And this comes out to minus 465 Newton meters, the work done on the sled by the kinetic frictional force. So we calculated the work done by each of the 4 forces on the sled during this displacement. Now you might ask, what does the work mean? In physics, work, we say, is something that transfers. When work is done, it transfers energy to or from the object that the work is applied to. If it's a positive work, as it is for the tension in the rope, then the transfer is to increase the energy. So 727 Newton meters of work, that means we've increased the energy by 27 joules. Remember, Newton meter is a joule. The negative work here, though, done by the frictional force, that means we extracted or removed energy, minus 465 joules from the object. Now, we're going to learn more about energy in the second part of this chapter, but in general, there's a couple types of energy. One is kinetic energy, and as you gain more kinetic energy, you speed up. Or if you lose kinetic energy, you slow down. Of course, for the object in question, it's the total amount of work done that determines whether you're going to have a positive input of energy into the system or a negative removal of energy to the system.